Hi everybody, today I want to talk about linear inequalities. You've seen before linear equations, and we've dealt with equations several times. So if I had 3x plus 5 equals 15, that's a linear equation, and that happens to be a linear equation in one variable. But now let's add a y to that. So let's say I had 3x plus 5y equals 15. Again, a linear equation. It's an equal sign, meaning that this side, the left side, must equal the right side. So what we're dealing with now is the same idea, only it's called, our linear inequalities, meaning that they're not equal. So either they're going to be greater than, less than, greater than or equal to, or less than or equal to. So those are our options. So what happens here is now 3x plus 5 could be greater than 15. Or maybe I had a problem in two variables where 3x plus 5y is less than or equal to 15. All of these now are what we would call our linear inequalities because it's either greater than or less than. And in this case, we have a less than or equal to option. So let's try our first example. In our first example, we have our 3x minus 2y is less than or equal to 12. Well, if I look at this and I think, all right, I have an x and a y, the best way to solve this is by graphing, to show a graphical representation. Now, we're going to graph it and we're going to have some shading involved because there's actually an infinite number of points that could be, that I could plug in for x, times it by 3, minus 2 times another coordinate of y, which would be less than or equal to 12. So there's infinite number of points where that could be. So let's solve for y. So we're going to subtract our 3x, subtract 3x. So then I get, you can go back to red here, negative 2y is less than or equal to negative 3x plus 12. You notice that I'm already getting it in this y equals, or in this case less than or equals, mx plus b form. Saying 12 minus 3x isn't incorrect. I just like putting the x value first, the x term first, so I can just have it in this form so the slope and the y-intercept pop out at me. So now I'm going to divide by a negative 2, divide everything, distribute that division up. And because that's negative, as you probably heard before, I need to flip the inequality sign. So just to reiterate here, because the value I divided everything through by is negative, I got to flip that sign. So now I have y is greater than or equal to 3 halves x minus 6. Okay, so I am going to graph that. The best way to show my solution is graph it. So bear with me while I get some little tick marks in here. Alrighty. So now what I'm going to do is I see I have my y-intercept of negative 6. So 1, 2, 3, 4, 5, 6, make my point. I have a slope of 3 over 2, so I'm going to rise, and do this in green to show the rise. 1, 2, 3, run 1, 2, and plot my other point. And because it's greater than or equal to, I'm going to actually have a solid line. Now, if I didn't have that equal to option, I would actually have a dashed line showing that I couldn't equal the line. Now at this point, I can see it visually where I see y is greater than, so I think I look and I'm going to go ahead and shade above the line or above, heading in a positive direction for the y's. So I'm going to shade right here. So to me, it looks a little bit obvious, but some people might be like, oh, that doesn't seem so obvious to me to shade above or below. So I'm going to do a test point, and the best one is 0, 0. So unless my line is going through 0, 0, 0, 0 is the best to plug in. So it should work. 0, 0 is in the shaded region. So it should give me a true inequality. Because remember that shaded region are all the points that would work. So 0 is greater than or equal to 3 halves times 0 minus 6. So 0 is greater than or equal to negative 6. And yes, that works. I got it. So I know I shaded the right area. So using a test point, that's what we call that, is really helpful. 0, 0 being the best, unless the line itself is going through that. All right, let's try another example. Okay, in this one, I now have two linear inequalities. And don't let that frighten you, because it's okay that there's two. I'm just going to, this is now what we would consider a system of linear inequalities. So in this case, I'm going to look for the shaded region where it's overlapping. So let's, let me get my little graph here, put my little tick marks so we can see everything. Granted, doing it on graph paper would be so much better with a ruler, but I'm just going to do it as is right now. So again, let's do green for the first one. I'm going to subtract x. I end up with y is less than or equal to negative x plus 1. That gives me a y-intercept of 1, a slope of negative 1 over 1. So I'm going to go down 1 to the right 1. Here's my other point. And it's less than or equal to, so it's going to be a solid line. And it is y is less than, so I am going to shade below. And again, you can go ahead and put in a test point to make sure you shade in the right area. Okay, so let's do blue for the next one. So I'm going to subtract x. I get negative, don't watch those negative y is greater than or equal to negative x plus 2. And now I'm going to divide everything through by a negative 1, which because I divided by a negative, that means I now have to flip the sign. So now it's y is less than or equal to x minus 2. That puts me at a y-intercept of negative 2, a slope of 1 over 1. So I rise 1, run 1. And it's less than or equal to, so therefore it's a solid line. And again, I'm going to shade below. Now I see the overlap in shading region, and I'm going to just go ahead and darken that in. And this area in black is going to be the solution to my system. So what does that mean? It means that any point in this shaded region, if I plug that xy coordinate in for here and here, I would end up with a true inequality. So again, it's got to work for both inequalities. All right, let's take on this next one. This is going to be a really interesting one. There is a lot going on. So you can see I kind of stepped it up as we went along. We started with 1, and now we have 4. In this particular system. And again, I'm looking for that overlap in shaded region that works for both of them. So starting with this one, I'm going to add 2x, I end up with y is less than or equal to 2x plus 4. So that is going to give me 1, 2, 3, 4. That's my y-intercept. I'm going to now rise 2, run 1 for my slope. It's a solid line because it is less than or equal to. So here we go. And I'm going to shade below. All right, the next one. Let's do this one in blue. I don't like how it's written, so I'm just going to rewrite that. Y is greater than negative x plus 2. It makes it look so much nicer to me. So then I have a y-intercept of 2. A slope of negative 1 over 1, so it's going to go down 1 to the right 1. Make my other point, but this is tricky because now notice it is y is greater than. I don't have a greater than or equal to option. So in this case, my line is going to have to be dashed. And that dash represents that it cannot equal that line. So here we go. And it's y is greater than, so it's going to be above. All right, so let's go in green for this one. X is greater than or equal to 1. Well, x equals, if I had x equals 1, it would be a vertical line where all of the x values are 1. So it doesn't matter what my y is, my x is always going to be 1. So there we go, make that a little bit straighter. It's a solid line because it is greater than or equal to, and greater, where are the x values greater? Well, they're greater to the right, so I'm shading to the right. Finally, I have this one, y is greater than or equal to 0. Again, if it looked like y is equal to 0, I would have a horizontal line. This is going to be a solid horizontal line right here because it's greater than or equal to. And where are the y values greater than or equal to? They're greater than or equal to above. But I'm not done. What I'm looking is where it is overlapping for all of them. So I'm going to go in black here, and I can see that right here, and continuing to shade, I can see that I am less than the red line. I am to the right of the green line. I am above the blue dashed line, and I'm also above the orangish line. And so right here would be the solution to my system for all 4 of these linear inequalities. So I hope you found this video helpful. Again, knowing that graphing linear equalities is really not that much different than graphing a linear equation. Just recognizing that with the greater than or the less than, that we now have to have the shading to actually represent the infinite number of solutions to that particular inequality. So I hope you found this video helpful.